The Milky Way contains more than 100 billion stars and is just one of 100 billion galaxies in the universe. How do these giant structures form, and more importantly, what happens when they smash into each other? I'm Dr. Alfredo Carpinetti, and I'd like to take you on a journey through the cosmos as we explore the past, the present, and the future of galaxies. My research has focused on galaxy evolution throughout the ages of the universe. Galaxies are one of the key features of our incredible cosmos, the true link between the relatively small and the infinity of the universe. To understand galaxy evolution, we need to understand what moves the universe, how it started, what its components are. We'll learn about the first stars and the first galaxy, and we'll see how diverse and peculiar the heavens really are. This is Smashing Galaxies. Humans have always considered themselves in a special place in the cosmos. It came as quite a shock realizing how far away the stars were. And it was even more shocking in the 1920s to discover that almost all the stars we could see with our naked eye were only part of our corner of the universe, the Milky Way. Suddenly the heavens were populated by many island universes, which we now call galaxies. But what are galaxies? Galaxies are a large collection of stars, gas and dust. They are found alone or in groups. They spin and move across the sky over millions and billions of years, while inside them stars form and die. Let's present the main protagonists of our story. Galaxies are classified in two main categories: early types and late types. Early types is just another name for elliptical and lenticular galaxies. Most of these galaxies are very massive and they have lived a long life. They have consumed most of their gas and are hardly producing any new stars. Lenticular galaxies tend to have a disk structure, while elliptical are just big balls of stars all orbiting the center of mass, but on different planes. Next, among the late types, we find irregular and spiral galaxies. Spiral galaxies have young disks made of gas, dust and star, and spherical cores that are made mostly of older stars. Sometimes the core is not shaped like a ball, but more like a bar. Spiral galaxies tend to be blue due to new star formation. They can produce a lot of stars every year. Last but not least, we have irregulars. These galaxies have no symmetry. They're mostly made of young stars and gas clouds, and their shape comes from close encounters with other galaxies. In fact, they're sometimes referred as flybys. Now we have a menagerie of galaxies. The question scientists wanted to answer is how they came to form. Why are there different types? The classification was put forward by Edwin Hubble, who first observed and estimated the distance of galaxies in the 1920s. Hubble discovered that these galaxies were not only outside the Milky Way, but they were also all moving away from us. This estimation was possible thanks to the Harvard computers, which were not some steampunk calculators, but a group of tireless women who classified by eye every known star at the time. One of them, named Henrietta Swan-Leavitt, noticed that one type of star always had the same luminosity, and it only appeared dimmer because of the distance. She discovered the first standard candle in the universe, and helped us understand how big the universe really is. This discovery showed us that the universe was changing, and if everything was moving away from everything else, there must have been a time when everything was compressed in a single point. This idea was ridiculed for many years, but the joke name given to it stuck around. Hubble found the first indirect evidence of the Big Bang. About 13.8 billion years ago, our complex infinite universe was all compressed in a singularity, a point of infinite density. All that we can see was there. It happened here, 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 here. Our physics begin at 10 to the minus 37 seconds. That's 0 point followed by 37 0 and then a 1. At that point, the universe experienced a period of exponential expansion called cosmic inflation. And in an instant, the universe expanded by a factor of over a billion billions. How long did cosmic inflation last? Until 10 to the minus 32 seconds. We can't even comprehend such a short time, let alone measure it. Let's compare it to a distance. If this fraction of time was 10 centimeters, 1 second would be 93 trillion light years, about 1,000 times the size of the visible universe. Ever since inflation, the universe has continued to expand, although at a much slower pace. As the universe grows, things get very messy. Let's start by introducing the four fundamental forces in the universe. There's gravity and electromagnetism, which we're all familiar with. But there are others too which are only apparent at microscopic scale. There's the weak nuclear force, which is responsible for radioactive decay, and the strong nuclear force, which keeps the nuclei of atoms together. In the same way that electromagnetism is transmitted by photons, the particle of light, the strong nuclear force are transmitted by particles called gluon, because they glue the nuclei of atoms together. Now, at the very beginning, the universe is so energetic that these forces were acting as one, and so far we don't know exactly how that would work in details. Physics get on a more secure footing around 10 to the minus 11 seconds after the Big Bang, when gluons and quarks form a plasma, a state where temperature and pressure are high enough to push particles together, overcoming the repulsive force between them. This was even hotter than solar plasma. The quark-gluon plasma was a state where no atoms, just quark and gluons floating around freely. CERN and our laboratories are currently exploring this extreme condition. Things get better around a microsecond after the Big Bang. Protons and neutrons, the particles at the center of atoms, start to form. But the universe is still too hot for full atoms to form. This process is called nucleosynthesis, and as the name suggests, it's when the nuclei of the lightest atom, hydrogen and helium, formed. It happened between 100 and 300 seconds after the Big Bang, so only the smallest nuclei had time to form. Normally, the protons and neutrons in atoms are surrounded by a cloud of electrons. Electrons can escape the grasp of protons if they gain enough energy, and they can steal such energy from light. For a long time, the universe was so hot, producing such high energy light, that electrons and protons could not join, even in the simplest atoms. As the universe grew bigger, it cooled down. Just think about a deodorant can after you spray yourself. The gas inside has more room, because some gases left, so the pressure is lower, so particles take longer to bounce around. You can feel the can becomes cooler in your hand. After nucleosynthesis, every time an electron got together with a proton to form a hydrogen atom, a photon, particle of light, would jump in and rip the electron away. But about 370,000 years after the Big Bang, the universe had expanded enough so it was cool enough for hydrogen to form. Suddenly, all those energetic photons were free to move around without being stopped. The universe had become transparent. However, those photons are not gone. They're still here, but we can't see them with our naked eyes because the universe has expanded so much. When those photons became free, they were visible light at a temperature of 5,000 degrees. Due to the expansion of the universe, they're now microwaves, corresponding to a temperature of 2.7 Kelvin, or minus 270 degrees Celsius if you prefer. Today, we call that light the cosmic microwave background. How the cosmic microwave background was discovered is a funny story. Two young physicists were trying to get rid of static noise on a big antenna at the Bell Laboratories in the States. One physicist thought it was bird poop on the antenna, so they had to scrub it clean. And yet this noise signal was still there. They then realized that the signal was coming from outer space. What they discovered was the cosmic microwave background, the CMB. Let's take a look at the map of the CMB. What are you seeing here is a two-dimensional map of the full sky in microwaves. The difference between the blue areas and the orange areas is just 1/10,000 of a degree. The universe as a whole is pretty much the same everywhere. But those tiny differences are important. They show us the gravitational anomalies that created gravitational potential wells for matter to fall into, and they are the places where galaxies are eventually formed. If we'd been there, the universe would have been completely devoid of visible light. For this reason, this epoch is known as the Cosmic Dark Ages. Surprisingly, we know more about the CMB than the period which followed it. Our instruments are still not good enough to probe that mysterious time, but we're getting there. And although there are many unknowns, we have some ideas about what happened. In the last 6 years, we have learned that there's much more of the universe that we can't see than the universe that we can see. Me, you, planets, stars, cows represent only 4% of the energy matter content of the universe. The rest is dark matter and dark energy. Dark matter makes up 26% of the universe. It surrounds us, penetrates us, and holds the galaxy together, just like the Force. We know very little about the true nature of dark matter, so midichlorians are an explanation as good as any for it. Dark matter is a type of matter that cannot be seen. It doesn't emit or absorb light, though it has mass and interacts with gravity. Without dark matter, galaxies wouldn't be able to keep their shape. Galaxies tend to have 10 times more dark matter particles than normal matter. There are alternative explanations to dark matter, but so far none of them have been able to be as accurate in predicting what we see in the universe as dark matter has. And then there's dark energy. Dark energy, sometimes called vacuum energy, is responsible for the accelerated expansion of the universe. It makes up 70% of the energy content of the universe, and we don't know what it is at all. Now the universe was and is dark, but let there be light. The new light in the universe after the CMB comes from the first population of stars. They form about 150 million years after the Big Bang, and although they no longer exist now, they affected the environment of the early universe. The way stars form have not changed since the very beginning. You take a large cloud of hydrogen and you let it cool down, so the cloud becomes denser. When it's dense enough, it collapses under its own weight. Gravitational collapse heats up the cloud again, but it's so quick that it generates nuclear fusion. Voila, a star is born. So, what makes the first stars special? They were made almost exclusively of hydrogen. We mentioned that the vast majority of matter was hydrogen. The most common element was helium, and even nowadays they continue to make the most of the visible matter in the universe. But what about the other elements, like oxygen or carbon? In astronomy, these elements are called metals, and they were formed by these first stars and helped create new stars. Metal makes it easier to form stars. Adding metals cools the gas cloud quicker, they collapse faster and create smaller stars. Without metals, the average size of the star could have been significantly bigger than our Sun. We're yet to observe one, as we can't really be sure, but most people agree that the range of mass could have gone from slightly less than our yellow companion to a staggering 1,000 times more massive. Some hypotheses expect that they could even be 10,000 times more massive. Stars of this size had short lifespan, and when they did explode, they generated spectacular supernova and left behind massive black holes, which probably merged to form the supermassive black holes that reside within the core of most galaxies. Now, these massive black holes formed by the first stars are not matter of speculation anymore. We observed them, or at least we saw the gravitational waves from two of these black holes merging. The mergers between the black holes that LIGO was able to detect was between a black hole weighing 36 solar masses and one that weighed 29 solar masses. Today, stellar black holes reach 15 solar masses at most, so these are definitely something different. Gravitational waves can be thought as analogous to electromagnetic waves, but while light is absorbed, gravitational waves cross the universe unchallenged, stretching and compressing space-time itself. There are no shadows that shield us from gravity. Today we're limited when we look towards the beginning of the universe. At present, the furthest we can see back in time is the CMB, but gravity allows us to look beyond the veil to see what happened right after the Big Bang. Obviously, this is the first step of a brand new technology. Maxwell and Faraday had no idea how their laws of electromagnetism would go to revolutionize society. But with a critical eye on the past and a good dose of hope, we can dare to dream of the wonderful things awaiting us in our future. Another important feature in the history of the universe is the birth of the proto-galaxies. A proto-galaxy is a gigantic cloud of gas stretching over many thousand light years inside dense clumps of dark matter. Inside these gas clumps, gravity reigns supreme, collapsing huge chunks of gas into the first stars. This is the free-fall stage, where the central region of future galaxy begins to form. In the last 30 years, we were able to observe only a few dozen of these proto or primeval galaxies, which mostly looked like shapeless blobs with an intense UV emission. During the local collapse, another phenomenon is taking place. Due to the influence of other nearby protogalaxies, the gas acquires angular momentum, and the protogalaxy flattens out into a disk, where the density fluctuation will eventually form the spiral arms. We have a timescale for the formation of spiral galaxy. The oldest spiral galaxy ever discovered, photographed here, is 10.7 billion years old, so the formation processes are extremely quick. Well, in cosmic scale. Now, having classified many galaxies, Hubble believes that early type galaxies were the first one to have formed, and over time they flatten out, grab gas from the intergalactic medium, forming their spiral structure around the elliptical bulge. Based on the limited data that was available, Hubble's idea of an evolutionary sequence for galaxy was very close to the mark. Galaxies do evolve and change from one type into the other, not in the way Hubble thought, from early types to spiral, but the other way around. Obviously, we've seen that one of the first galaxies was a spiral galaxy, so we've known that this object formed first. So how do we go from spirals to elliptical? That's through galaxy mergers. Mergers are violent interaction between galaxies. They are considered to be one of the fundamental steps in galaxy formation evolution. Mergers occur when two or more galaxies collide. This interaction can radically alter the overall structure of the parent galaxy, the progenitors, due to the tidal force between the galaxies and the friction between the gas and the dust that gets moved around during this process. If two galaxies of approximately equal size collide at suitably wide angles and relatively low speed, then their shape, if they're elliptical or spiral, they're changed forever. This is called major merging. However, if one of the galaxies is significantly larger than the other, the larger one will often eat the smaller one, absorbing most of its gas and stars, while the larger one remains mostly undisturbed. This is often referred to as galactic cannibalism or minor merging, where the mass ratio between the two galaxies is less than 1 to 3. Each galaxy will go through at least a major merger and several minor merger events during its lifetime. While only major merger can irreversibly alter a galaxy, both major and minor event can produce clear changes in one of our objects. You see, during a merger, the intense tidal forces the galaxy experiences are so powerful that they compress the gas and dust through the galaxy, creating in both old and young galaxy a new age of star formation. This is quite the telltale for older galaxies. Suddenly they become bluer, more active, and their change in shape and color is a beacon for astronomers. Something went on there. In the early stage of many mergers, you suddenly see large red clouds, birthing dozens of stars every year, as well as a large collection of blue stars, the hottest, biggest stars formed in the starburst phase. These blue stars are important. They form quickly and die just as quickly in spectacular supernova explosion. The gas is usually recycled to form new star, but in mergers, after a few 100 million years, star formation is quenched. The culprit of the quenching is the supermassive black holes at the center of most galaxies. Being sucked in is only one of the many ways a black hole can mess you up. During mergers, the black holes can become very active. Gas, dust and other debris accumulate around the central black hole and form an accretion disk, a ring of material that surrounds the black hole. The material is then accelerated, pulled and stretched by tremendous gravitational pull, which heats it up to millions of degrees. During its active period, the accretion disk around the black hole at the center of NGC 4889 would have emitted up to 1,000 times the energy emitted by the Milky Way every second. The black hole would have produced powerful jets that expel material from the disk and heated up the galaxy and its surrounding. This process is tragic for star formation. You see, for stars to form, the gas needs to be cool. At least cool enough to contract into a cloud, which can collapse on itself due to gravity. The material ejected by the black hole jumpstarts a feedback mechanism from the mergers, generating galactic-wide winds, heating up large molecular clouds, where star forms, and thus snuffing out all star formation. So there we have it, a picture of galaxy evolution, by far not complete, but solid enough for us to make a prediction of both the past and the future. We know that galaxies tend to form with regular shape, so any deformation, any variation is due to the event in their past. The magnitude of the quirkiness can tell us a lot about the type of interaction a galaxy might have encountered during its lifetime. We can look at galaxy close and far as spot indication of flybys, major and minor mergers, and we can see how the interaction has shaped our little corner of the universe. The Large Magellanic Cloud, which is visible in the southern hemisphere, is one of the satellites of the Milky Way, and although it might look completely messy, it's actually disrupted by a spiral. And even the Milky Way itself has already cannibalized at least one other satellite. What's left of this bygone galaxy is called the Sagittarius Stream, a last vestige which now coils itself like a snake around the Milky Way. So galaxy evolution tells us about the past, but what we can say about the future? Well, the Milky Way is not going to look the same forever. We can actually estimate when the change will take place and will be spectacular and potentially catastrophic. The chance that the Sun will be affected is quite small. Most likely the solar system will continue to move around, but on a different orbit. Andromeda, the largest, closest galaxy to the Milky Way, is coming for us, and it will be the major merger will completely disrupt both galaxies. The two objects will twist and turn under each other's force of gravity, with new stars shining and old stars dying. The familiar stretch of stars across the sky will vanish and replaced by a large spherical core of new stars. We will then, in about 5 billion years, inhabit a new elliptical galaxy. In our adventure through time and space, we had the chance to meet the Galaxy, and they are really an incredible bunch. Galaxies are more than a big aggregation of stars bound together by gravity. They are as diverse as you and me. Thin, thick, blue, red, yellow, very regular, irregular, and some are a complete mess. There are about 100 billion galaxies in the visible universe, each with 100 billion stars. These cosmic islands are born and change, bound, pulled and spun by the same forces which keep us firmly on the ground, the forces that moves the sun and all the stars. Using physics we have learned so much about this phenomenal object, and yet we only started to understand them less than 100 years ago. I wonder what we might find out 100 years from now.